It's the time of the year again where we do a paper analysis of the chemistry O-level practical exam. For this year, there are 3 experiments. The first one is a thermometric titration. The second one is a gravimetric analysis. And what's a practical exam without qualitative analysis? Now for this year, I know I've said this many times before, but the experiments are pretty straightforward. And usually for years where the experiments are straightforward, the questions will be a bit more difficult or tricky, but this year the questions were very straightforward. So I think the setters for this paper would have found a lot of aura by setting such a paper. So the first experiment is a thermometric experiment where we are supposed to mix different volumes of solution A with solution B and we measure the temperature change. This is a standard thermometric titration experiment. However, it's a bit tedious. I don't know whether you have learned this before, but there is a time-saving hack for such thermometric experiments, and the hack requires you to perform the experiments not in numerical order, but in the following order. You start with experiment 1, followed by experiment 7, and then experiment 2, followed by experiment 6, and so on. Now, why is that so? It's because for this experiment, the slowest step, or in higher levels, we will learn this in kinetics, called the rate determining step of this experiment, is the filling up of burette and measuring out of liquids using the burette. So if you were to follow the sequence that I've mentioned, you only need to fill up the burette completely 4 times. And that will minimize the time taken. Now, why is that so? Now, assuming that you fill up a burette completely, you would have 50 centimeter cube of solution. So after experiment 1, you would have used up 40 and you have 10 left. So instead of filling up again, you could have used the 10 remaining for experiment 7. Alright, then you fill up the burette again, and for experiment 2, you would use up 35. And then you have 15 remaining where you can use for experiment 6 and so on. Alright, so if by alternating the experiments 1, 7, 2, 6, 3, 5, you only need to fill up the burette 4 times, and that will cut down on the time taken for the experiment. Now, having said that, there are 2 common mistakes from experience when you are doing thermometric titrations. The first of which is less serious. The second one is a bit more serious. The first one is where your teachers have painstakingly reminded you time and time again that when you fill up the burette to remove the funnel after that. Okay, but I'm quite sure if you were to look around the lab, you will see many super trees. Alright, that's why you have the super tree diagram in the slide over here. And that represents the funnel being left on top of your burette. Okay, when you do that, the solution will continue to drip into your burette as you are measuring out the liquid. And therefore, your volumes are going to be slightly more by maybe 0.1 or 0.2 centimeter cube. Okay, but the good thing is this, given that thermometric experiments are not very accurate to start with because of the heat loss to the surroundings, and also because when you draw the best fit line, any small inaccuracies will be averaged out. The effect is not going to be very significant. The second common mistake is more criminal. Okay, and it goes something like this. For example, you want to measure out 25 centimeter cube of A. Okay, so a student may fill up to the 25 centimeter reading on the burette, and they open the tap and drain the entire burette, thinking that they have measured out 25 centimeter cube. Alright, but you need to remember that there's this extra part at the bottom of a burette. So to measure out 25 centimeter cube, we are supposed to stop at the 50 centimeter mark and not drain out your entire burette. That is a common mistake which I think some of you may have made in the exam. For that, you would have added a lot more solution than you're supposed to add. So if you have done the experiment properly, you will definitely see this trend. From experiments 1 to 4, the temperature rise would increase, and then from 5, 6, 7, it will decrease. That is standard for a thermometric titration. So if you were to plot the graph, you will get two straight lines which intersects at a point. And what's important at this point of intersection is the volume of B, because that would give you the titer value, or that represents the end point of the titration. So if you have done everything correctly, you should get a volume of maybe 27.5. Now, for this year's practical, they didn't state to start the graph from the origin, but it's standard for thermometric titrations to start the graph from origin. Why is that so? Because when you have 0 centimeter cube of B, that means you entirely A, 50 centimeter cube of A and 0 centimeter cube of B, the temperature rise will be 0. Alright, so by right, the origin should also be a data point, which is usually stated in the O-level instructions, but not for this year. So I don't know whether they're going to mark the origin as a data point, but for thermometric titrations, the origin should also be, the graph should pass through your origin. After finding the titer value, the calculations are pretty straightforward. Usually for titration calculations, there is a story behind the titration. You need to understand the story and then to solve the question. But for this year, it's the most basic of chemical calculations, which can be solved simply with the 3C method that I've been teaching in my lessons. What is the 3C method? Number 1, convert to moles. So from the volume of B, we can find the number of moles of sodium hydroxide. Second C is to compare mole ratio. 1 mole of sulfuric acid reacts with 2 moles of sodium hydroxide. So the number of moles of sulfuric acid is half the number of moles of sodium hydroxide. Third C is to convert from moles. So convert from moles to whatever the question is asking for. The question is asking for concentration, so you divide by volume. Right, for this question, the question states strictly to leave your answers to 3SF, so you need to round it to 3SF. The qualitative questions that follows the calculations are also pretty straightforward. You are asked to predict the sign of your enthalpy change. We have learned that acid-base neutralization reactions are exothermic, so you just need to state that it's negative, delta H is negative. Why? Is because the temperature of the solution or temperature of the surroundings increases. Next is one of the 2 common type of qualitative questions that you will get in a practical exam. The first type is where you are required to identify a source of error and how to rectify the error. The other one is where they change a parameter in the experiment. They change the variable in the experiment and ask you to predict how would it affect the experimental results. So in question E, the question is where you change the concentration of B to 1 mole per dm cube. So all you need to do is to compare with the original concentration of sodium hydroxide, which is 1.3. So now with a lower concentration of sodium hydroxide, the volume of B required to reach the equivalence point would be higher. All right, because the concentration lower, you require a larger volume to reach equivalence point. Experiment 2 is a gravimetric analysis question. We are given an unknown sample C, which is a hydrated metal salt. We are supposed to heat the solid strongly for a period of time, and we are supposed to measure the change in mass of the solid. And from there, we are given a formula to calculate the percentage mass of metal in C. So again, this should be a pretty straightforward experiment, except that we are using an unfamiliar apparatus, which is your crucible with lead. Now, actually, school labs should have been equipped with crucible with leads, just that we haven't used them in like the past decade or so, and they are primarily the house or the home to spiders and many other insects until we forcefully evicted them for this exam. So, but still, it's a pretty straightforward experiment. We could have easily replaced the crucible with a boiling tube. It should have worked as well, but I think in this exam, the examiner wanted you to be able to handle certain apparatus in the lab. Now, in practical lessons, we have learned that when you heat a solid strongly, we are actually trying to decompose the solid. And in our syllabus, thermal decomposition, we learned that in reactivity series, we learned that metal carbonates decompose on heating to give you metal oxide plus carbon dioxide. Okay, so very likely we are looking at a metal carbonate as C. Then when you are heating the solid strongly, I'm sure you have noticed this is quite obvious. The solid was initially white. When you were heating it, when it's hot, it became yellow. When it's cooled down again, it turned back to white. Now again, in the chapter of reactivity series, you would have learned that that is an observation that you will get when you have zinc oxide. Zinc oxide is white at room temperature. When it's heated up, it becomes yellow. It turns back to white when it goes back to room temperature. Okay, so from the observations, you would be able to predict that C is actually zinc carbonate. Okay, the calculations again are pretty straightforward. There is no trickery in there. So all you need to do is to find the mass of C, find the mass of solid after heating, and then substitute the two values correctly into the formula given, and you should get a percentage of about 58 to 60%. Again, it may vary from exam center to exam center, but this is the rough value. The question goes on to ask about one change for a more accurate result. So for gravimetric experiments, we know that in order for accurate results, we must make sure that the solid has fully decomposed. So one change would be to heat the solid for a longer period of time. Right? In an actual research, what we usually do is to repeat the heating, cooling, weighing cycle many times until we get a constant mass. So you heat, cool, weigh, heat, cool, weigh, heat, cool, weigh until you get a consistent reading, mass reading. That means that the solid has fully decomposed. But I think for this question, all you need to state is to heat for a longer duration. Y is to ensure that all of C has decomposed. Now, when I first saw this question, I was a bit puzzled as to why the formula for the percentage mass is given, which makes the question a lot easier than if you were to calculate from scratch. But then I realized the reason for that is because they coupled the gravimetric analysis with qualitative analysis. Okay, and if we were to want you to calculate from scratch, then we would have to tell you that C is zinc carbonate. Right? So to avoid that, because of the coupling of your gravimetric analysis and qualitative analysis, the examiner had no choice but to give you a formula, and then all you need to do is to substitute the values in the formula, which makes the question a lot more easier. For those of you who are interested how the formula comes about, I will show you how, but it's going to be very boring. You are better off growing a garden or something. If you want, you can skip the next part. So as mentioned, when you heat a metal carbonate, it's going to decompose to give you your metal oxide plus carbon dioxide. the question states that it's a hydrated metal salt, so I assume that water vapor will be given off as well. So based on the measurements that we make in the experiment, right, or if we assume that the decomposition was complete, the mass of the solid that we get after heating would be the mass of zinc oxide. So with the mass of zinc oxide, we can go on to calculate the number of moles of zinc oxide. Okay, and from the equation written above, you can see that number of moles of zinc is equal to number of moles of zinc oxide. So, and then we can multiply by the atomic mass or the molar mass of zinc to get the mass of zinc. So we get this expression over here. And then to find the percentage by mass of zinc in C, we take the mass of zinc divided by the mass of C times 100. So if we were to simplify the expression, we will end up with a constant of 80. So that's how the formula came about. The last experiment is a QA experiment. Again, QA do not come more simpler than that. Okay, the first part of the QA, you're supposed to mix C and D. C is a white powder. And for those of you who were alert enough, you would have guessed that it's zinc carbonate. D is a solution. You're supposed to add a solution to a white powder, and the question requires you to test for a gas. That should scream at you what gas you should be testing for. I repeat again, you're adding a solution to a white powder and you're asked to test for a gas. Obviously, that must be adding an acid to a carbonate, which will give you carbon dioxide gas. So the required observations will be effervescence, colorless, odorless gas form, gas produce a white PPT with lime water, gas is carbon dioxide. Now I know many of you are going to throw your arms in the air and say that I didn't get the white PPT. Alright, this is not uncommon given that the amount of solid given is very little and the effervescence is very rapid. Okay, so if you were to anticipate carbon dioxide being produced, you have to prepare your lime water and delivery tube in advance. Okay, and almost immediately after adding D, you should cap the test tube with your stopper. All right, and you should rock the test tube back and forth, right, to push the carbon dioxide into the lime water. Okay, which I think many of y'all did not react in time. So if you wait 1 or 2 seconds, the carbon dioxide will be all gone. Okay, another possible mistake is where you use too much lime water. When you use too much lime water, it's going to take a lot more carbon dioxide before you start to see the white PPT. Alright, so the recommended would be about maybe 2 to 3 centimeter depth of lime water that would be sufficient. So from the fact that we got carbon dioxide when we added C to D would confirm our suspicion that C is a carbonate and also allow us to deduce that D must contain hydrogen ions, or D is an acid, okay, which seems to match the description given in the question where C, the cation and anion in C are listed in the QA table and only one ion in D is listed in the QA table because hydrogen ions are not listed in the QA table. We were then required to perform 2 tests on E and 2 tests on D. And I'm going to say this again, that QA does not come easier than this. The test on E is the very first thing that we learn in QA. We add sodium hydroxide dropwise in excess, followed by aqueous ammonia dropwise in excess. Both gives a white PPT soluble in excess to give a colorless solution. So that confirms that our cation is zinc. Again, we know that it's carbonate already from earlier. Alright, so what's left is the anion in D. Now, we are supposed to add nitric acid followed by barium nitrate, and then another test, nitric acid followed by silver nitrate. Again, these are the very basic tests that we learned in the test for anions. So you should have no observable change for barium nitrate, which means that sulfate is absent. I think some of you are going to write no PPT form. That's when you don't read the instructions carefully. The instructions say that if there are no change, you write no observable change. I don't know whether they are going to accept no PPT form. It really depends on the mark scheme, but I think generally it should be okay. For silver nitrate, you get a white PPT, which goes on to confirm that the anion in D is chloride. So there. Again, the tests are pretty straightforward. You should be able to complete this very, very quickly and arrive at a conclusion very easily. The last question is a planning question. The question describes a metal displacement reaction where if you add iron powder into copper 2 sulfate solution, you end up with iron sulfate plus copper. And the question goes on to describe that the iron sulfate can be either iron 2 sulfate or iron 3 sulfate, which we don't know, and you're required to plan an experiment to find out. Now the question also provides the method to you where you have to use 1 gram of iron and then determine the mass of copper produced. So that is a highly scaffolded question. The method is provided to you, and there are also many hints given in the question, which is why I always encourage my students to read, underline and annotate all the important hints. Now, where are the hints? Number 1, in the passage they said that when iron powder is warm with copper 2 sulfate, so you are supposed to underline warm and annotate that it has to be stated in your procedure. Okay, so in your procedure you need to mention warming of the mixture for the reaction to occur. The next clue is given in the first part of the question where you are supposed to balance the chemical equations. So this is also a very, very straightforward question. And in order to avoid or to make sure that you are on the right track, actually the setter has already given you the mole ratio between iron and copper. Okay, so they provided very clearly over here that when iron 2 sulfate is formed, you have 1 mole of iron reacting to form 1 mole of copper. And if iron 3 sulfate is formed, we have 2 moles of iron reacting to form 3 moles of copper. So that is a difference which we can use to find out which product or which reaction takes place. So that's clue number 1. Next, you're supposed to again write the balance equation, but it's very easy. The state symbols you simply need to copy from above. Solid aqueous, iron 3 sulfate is also aqueous. We learned that in the solubility rules. And then copper is solid. And then to balance the equation, again, it's very simple. If you balance copper, you add a 3 over here. Okay, and for the formula of iron 3 sulfate, you should have learned it in ionic bonding, or you should have learned it in chemical formula. It will be Fe2SO4 bracket 3. So the third hint given in this question is in the state symbols. They are trying to tell you that in the products, you have a mixture of a solid and an aqueous solution. So in order to separate the solid from an aqueous solution, it's again very simple. You just need to perform a filtration. So from the hints given, from the method that they have prescribed, it makes the planning actually very straightforward. I have no idea how detailed they want the procedure to be, but this is a highly detailed one. where every apparatus and every step is shown. So as mentioned, you need to state the apparatus and the measurements that you need to make. So you need to use an electronic balance, weigh 1 gram of iron powder, right? And then you add it into copper 2 sulfate solution in a beaker. You need to warm it over a Bunsen burner and you need to stir it for 2 to 3 minutes. Filter the mixture to obtain copper metal as the residue. Wash and dry the copper metal, and then lastly to record the mass of copper obtained. This question is a type of quantitative question. So in quantitative questions, a feature in the procedure is that your whatever sample that you have, you must react completely. So I would think that one key point that I would look out for as a teacher is that you must mention that is added into excess copper 2 sulfate. But for this question specifically, I don't know whether that's important because the question already states to assume that all your iron will be reacted. Okay, so I don't know whether that with that you still need to state that excess copper 2 sulfate solution must be used. The next important key point in your procedure would be, of course, as mentioned, you need to warm, because the question states that the reaction happens when it's warm. Again, I don't know what goes into the mark scheme, but as a teacher, I will look out for that because I've stated explicitly in the question that you need to warm for the reaction to happen. In a quantitative type planning question, the discussion would be the calculations that you need to make in order to arrive at the conclusion. Okay, so as mentioned, from the two equations is already a big hint to you that the mole ratio of iron and copper will be different for the two experiments. So the first calculation that you need to make is to calculate number of moles of iron or amount of iron by taking 1 gram divided by the molar mass or atomic mass of iron. Second calculation is to find the amount of copper, which is to take the mass of copper divided by the atomic mass of copper, and then to determine the ratio, the mole ratio of iron to copper. If the ratio is close to 1:1, it means that iron 2 sulfate is formed. The first reaction took place. If the ratio is more to 2:3 or 0.66, it means that iron 3 sulfate is formed. So as usual, I'm going to end by saying that this video is purely for education purpose, and I do not know what the mark scheme is. And please do not ask me how many marks will you get if you were to do this, if you were to do that. The practical is over. Do invest your time and effort now into doing your theory papers well. And once again, I'm going to end off with a cheesy quote. When the going gets tough, the tough gets going. Okay, all the best for your O-level exams.